Kumar Singh. So this is the fifth live session of the course Statistical Mechanics, which is being taught by Professor Dipanjan Chakraborty at over the NPTEL portal. And here we will discuss some, here we'll recap some of the concepts and solve some problems to help you in solving the tutorials, okay? And you can ask any general doubt or question that you have, and you can unmute and ask at any time, okay? So, okay, so let's start. Okay, so in this week we have concepts such as ensemble and what is macrocanonical ensemble is, and so I'll try to explain them a little bit so that you can understand really what it means. I mean, it is being taught in the lectures too, but I'll try to explain it a little bit more. But before going to that, I'd like to discuss a very important concept, okay, which is the connection of statistics and thermodynamics. So we have been studying the thermodynamics over the past 4 weeks, right? So what is the connection between the thermodynamics that we have studied and the statistical mechanics that we are going to study? Basically, the connection between microstates and macrostates. So as we know, what is a macrostate? So a macrostate is defined by variables such as number of particles, volume, and energy, right? So for a given system. But this macro state with given number of particles, volume, and energy can have various microstates, okay? So microstate is defined by the individual phase space coordinates, so qi, pi, okay? So these are 6n coordinates. 6n, if you have n number of particles here, so this will be 6n number of variables, and basically coordinates, 6n coordinate space, okay? So basically this is the position and momenta of all the particles in this macro state, okay? And it will keep changing, right? So consider a gas. You have a gas in a chamber, ideal gas or something, right? Now it has, suppose, n number of particles, which will be order of 10 to the power 23 Avogadro number, right? So it's a huge number of particles are there, but you can define a macro state. So its macro state is defined by these number of particles and its volume, right, and internal energy or E, whatever, okay? But the micro state, the actual position coordinates of these particles, these n particles, which is given by this qi and pi, it will keep changing, right? They will collide with each other, they will exchange energies, and all sorts of phenomena will keep happening, right? And so you have extremely large number of microstates. So macrostate is number of microstate is given by this symbol, okay, which depends on a particular macro state, okay? So that's why it is a function of n, v, and e. Now So now what do you think if you have a, so suppose you have a chamber separated by something, a wall here, which can exchange energy, but you cannot exchange number of particles uh, beyond this wall. Okay, and suppose you have a system here A1 and A2, a gas or something, right? So and it has n number of particles, it has n1 or n1 n2 number of particles respectively, and these can exchange energy. So E1 E2 can be exchanged. Now if I ask you when it will reach equilibrium, so that is, I mean, if it is left to itself, okay, when do you think the equilibrium will reach? Like how far will the energy exchange go, okay, in order to bring the subsystems A1 and A2 into mutual equilibrium? So when that will happen, can you guess? You understand my question? So it might be that E1 is greater than E2, right? So its temperature is greater than T2. So there will be exchange of energy between these two subsystems, and it will reach to an equilibrium, right? But that equilibrium, what is the condition? When the equilibrium will happen? If you want to talk about in terms of this, microstate. So if it has microstate omega 1 and it has omega 2, so and if the composite microstate is say omega 0 or something, so okay, if you don't know, it's okay. So that is what I wanted to discuss. So the equilibrium will happen, okay, such at a value of suppose E1. So I mean E1 plus E2 is equal to total energy of the system, okay. So if you fix E1, the E2 is also fixed because total energy is already fixed, right? Now what I am saying is so this equilibrium will happen when for a number which maximizes this number of macrostates, okay, when the number of microstates maximizes, okay, that will lead to a equilibrium state. Do you understand what I am saying? So this number of microstate, it will keep changing until it find a macrostate which affords largest number of microstate, okay. So basically when this maximizes, that's when the equilibrium will happen. And so mathematically, okay, so statistically speaking, we call a macrostate with a larger number of microstate, okay, we call a macrostate. So let me write it. Macrostate given by these variables, volume, energy and number of particles, with a larger number of microstate as a more probable state, okay. And the more probable state is what we call the equilibrium state, okay. And this is what equilibrium means. The state which is more probable is the equilibrium state. Okay, and I mean, there is a nice derivation, it has been done in the lectures. So this leads to this famous, formula by Planck of entropy, which is just this simple formula. So entropy is equal to K natural log of this microstate, number of microstates. K is here the Boltzmann constant. Okay. So it is I mean, very interesting that you can write an entropy of a system in terms of the macrostates. Okay, we have not seen that yet. So this is the connection between macrostate and a macrostate. So entropy is a macroscopic quantity, right? It is a quantity of a system. It is not a quantity of the molecule of a gas. It is an emergent quantity of the whole system. So this is a macroscopic quantity, and this is the microscopic, and this is the connection between macro and micro. Okay, so this is the connection between basically statistical mechanics and thermodynamics. Okay, and as you can see from this formula, if there is only one microstate, so omega equal to 1, entropy is 0. Okay, so 0 entropy here means that the system has only one configuration to take. It cannot take more than one configuration, then the entropy is 0. As this macro state starts increasing, okay, as you have more available choices in the system, the entropy increases. Okay, and so I mean, this is one of the manifestation.
It sounds like you
Sorry.
might.
Yeah, so clearly, I mean, so this is what we call disorder. So as you introduce disorder, as you increase the number of available macro states in the system, the entropy increases. So this is how you can understand disorder lead to more entropy. Okay, do you understand what I am saying, or you have any question to ask? Please ask any question if you have. Okay, if you don't have any question, then fine. So now let's try to understand what is an ensemble. Okay, so suppose yeah, so suppose you have given a system, okay, and you have to calculate its properties, and you know that this micro state keeps changing, okay, because these particles of the gases, they keep colliding. I mean, there is a it is always changing. So you have extremely large number of microstate, right? So this microstate is always a very large number. It's an extremely large number. Okay, and what you observe about a system is an averaged behavior over time. So that means so given a system, if you want to calculate some quantity about it, okay, you take an average over time, right? So sorry, right? Because so for example, if you calculate temperature, So temperature, or yeah, temperature. So if you have a temperature, so temperature is an it keeps changing for a system, right? And what you calculate is an averaged over time, uh, which is called, expectation value or whatever. Okay. And in which, the system passes through all the micro states that is available for it. Okay. So averaged over time in which system passes through all the microstates that is available. But but instead what we can do is, since we know that since we know that there will be extremely large number of microstates, extremely large number of configuration, what we can do is we can fix the time. Okay. So we can take a single instant of time and make ensemble. Okay. So ensemble is basically defined as, ensembles are mental copies. So you make copies of the system, of the given system. Okay. According to the number of microstates available. Okay. So this is what we call ensemble. So if you have given a system, suppose a gas enclosed in a chamber. Okay. You make copies, you make infinite copies of this system, where each of these copies will correspond to different microstates. Okay. And the collection of these copies which is what we call a ensemble. Do you understand? Okay, thank you. So yeah, so basically now we have the ensemble. So taking average over time is equivalent to taking ensemble average. So now you don't have to wait till infinity time to measure something. You can make an ensemble and make a measurement on these, taking average over all these ensemble. And that's what we do in statistical mechanics always. Okay. That's how it works. So we always make ensemble and we calculate our quantities, the observables, taking average over the ensemble. We don't do measurement over time. Okay. We don't have to wait for the, if you have a gas in a chamber, we don't have to wait till infinity, time equal to infinity, to see how many microstate it goes through. Okay. We can calculate all the microstates that is available using our probability and statistical knowledge, and then we can calculate average over those ensembles. So that's how things are done in statistical mechanics, as you will learn later when we solve some problems. Okay. So yeah, this is about the ensemble. And yeah, so some basic formula that I will try to write. So as I said, macrostate is defined by these phase space coordinates, and in phase space these are called representative points. Okay. And and this goes into continuous changes, so it keeps changing, as I mentioned, right? If you have a gas all the particles will keep changing its position and momentum, right? So it keeps changing, and so if you want to define a ensemble, so an ensemble will be, so suppose you have this uh, phase space, so your ensemble will be a swarm of representative points, right? So these are all representative points, and each representative point denotes a microstate for a given system. Okay, so it's a what we call a swarm, just like swarm of bees. So these are swarm of representative points. Okay, each current corresponding to a microstate of an ensemble. And then we can define something called density function. So like the probability density function that we studied last time. So density function is basically, at any time t, number of representative points in a small volume, say dq dp. You have to remember that the q here is, because it's x, y, z, 3 coordinates, p here is also px, py, pz, so it's total 6n coordinates, okay, for n number of particles. Okay, so this is a typical small volume dq dp, okay, in this phase space. So this is your phase space denoted by q and p axis. Okay, and so density function is basically defined as at any t number of representative points in a small volume dq dp is given by the density function rho of qp dq dp. Okay, and this is your basically your density function. So as its name suggests, is just the density of these representative points. Okay, that's it, the density. And if you want to if you want our ensemble to remain stationary, this density should not change as a function of time. So it should be 0. Del rho by del t is 0. Okay, and this is the equilibrium condition that I was talking earlier. Okay, so whatever you will calculate, the average value of any observable, it will remain independent of time. Okay, because your density function is not changing, so if you calculate an average of a quantity, it will be constant, it will not change. And there is something called Liouville's theorem. So I mean, this has been done in the lectures, but I will just write it out. So what Liouville theorem says is the total differentiation of this density function is 0, which leads to partial differentiation in as function of time plus the Poisson bracket of this density function with Hamiltonian is equal to 0. Okay, where the Poisson bracket, that it is given by this expression. I'll just write it out and I'll explain what this Liouville theorem actually tells you. So this is the Poisson bracket. Okay. So what Poisson bracket, what this Liouville theorem is tells you that basically the local density of the representative points this total density, okay, as viewed by an observer moving with the representative point, stays constant in time. Okay, so the density stays total density stays constant in time. That means this swarm of particles, I mean this swarm of representative point, as it moves through the phase space, okay, the local density, that means if you are moving through a particular if you're moving with respect to a particular representative point, you will find that the local density is constant. That means, so suppose now imagine imagine it like a fluid, okay, a fluid moving, water moving in a pipe, okay, something like that will happen here. So it is like a incompressible fluid. So it is not, the density, the local density is not changing. That means it is incompressible. Okay. So these representative points, when it moves through the phase space, it moves as a incompressible fluid. Sorry, incompressible fluid, not density. Yeah. So this is the physical meaning of this Liouville's theorem. It is called Liouville's theorem. Okay. Now we'll so in connection to this, there is a special type of ensemble which is called microcanonical ensemble. So what is this microcanonical ensemble? So now suppose you have a system whose energy, so energy is given by Hamiltonian in Hamiltonian of the phase space. It lies in a certain interval, so some constant E minus half delta to E plus half delta, okay, and where delta is smaller than, very smaller than E. So in the phase space it is a hypercell, okay, and the what is the microcanonical ensemble is, so the collection of systems for which this density function is constant, okay, constant given that the energy in the energy in the phase space, so Hamiltonian basically, lies in this hypercell, okay. So this basically means that its energy is confined to a particular range, okay. It cannot take arbitrarily any energy value. This is what it means basically. And for that case, its density function is 0 and constant, and it is 0 if its energy is anything other than this range, okay. And this constitutes a microcanonical ensemble, okay. Now there is then if you are given this, then you can calculate the entropy of such a system very simply. So suppose there is a volume of allowed phase space. So yeah, so now given this, yeah, you can see that the volume of the allowed phase space, that is, suppose, I mean, yeah, this is a volume omega of a phase space, okay. It will simply correspond to the number of microstates accessible to the system, right? Which is to say that suppose this is omega 1 and this is omega 2, the two volume of phase space is there. So the probability of finding you know, the probability of finding a, a, a particular configuration in this volume omega 1 is the same as finding another representative, similar representative point at omega 2. Okay, so that means the volume omega is directly proportional to the multiplicity uh, of the, I mean, macro state accessible to the system. Okay, and so this will leads to, I mean, you can write it like this, where omega naught is a constant which you can determine, and then we know that entropy is given by this formula, which is simply omega by omega naught. So now you see the entropy can be written as the space, phase space volume. Okay, omega. And one very good example of this kind of microcanonical ensemble is like a classical, you know, ideal gas, which is monoatomic ideal gas. So it has only one kind of particle. So these kind of system, the real life system, they behave as a microcanonical ensemble. Okay, so because their energy is confined to a particular range. Okay, they cannot arbitrarily take any energy value, and so the entropy for those kind of system is given by, you know, it is just it depends on the phase space volume that you are looking into. Okay, so yeah, I mean, this is just these are just simple formula that I wanted to discuss. Let's go over some problems, then it will become more clear. Okay, so if you have anything to ask till now, please do, otherwise we'll solve some problems. Is everyone fine? Hello? Okay, so okay, let's go to the then problems. So this is the first problem. Okay, it's a very simple one, so let's try to understand it. So consider two localized independent quantum oscillators with fundamental frequency omega naught and 3 omega naught. Okay, uh, yeah, then the total energy of the pair is given 10 h bar omega, and the question is how many macrostates are accessible to the system as a whole. So what question is what the question here asks is, so suppose you have, you know, two quantum oscillator, and their fundamental frequency is given, so you can write the energy. So you know that energy of a harmonic oscillator is given by this, right? So, and where omega is the basically the frequency, the fundamental frequency of the system. So suppose you have two system in A and B, so then energy of A will be h omega naught, and energy of B will be NB plus half h bar, and here the frequency is 3 omega naught, so I'm writing 3 omega in place 3 omega naught in place of omega. And what it says is that the total energy, that is EA plus EB, is equal to 10 h bar omega. So let's put these two here in this equation, in A plus half right? And this. Now if you solve this, you will get Na plus 3Nb is equal to 8. Okay, h cut omega will cancel, omega naught, sorry, this will cancel from all the three sides, right? And you will end up with this. Now what the question asks is how many microstates are accessible to the system. Now just now we discussed what is macrostate. So microstate are all those configuration which the system can take. Okay, so to get an energy 10 h bar omega, this Na and Nb are the energy levels, right? So what are the different energy levels? Like, so you have starting from n equal to 1, n equal to 2, n equal to 3, n equal to 4. It can lie anywhere, right? You have lot of options. So, but here the constraint is the total energy should be 10 h bar omega, and due to that constraint you have this equation. And now you see, if you have Nb is equal to 0, then Na should be 8. If you have Nb equal to 1, then Na should be 5, otherwise it will not be equal to 8. If you have Nb is equal to 2, then Na should be equal to also 2. Now you cannot have Nb equal to 3. If your Nb equal to 3, then it become 9, and which cannot be equal to 8 if you are adding another something here, right? I mean, so Nb equal to 3 is not possible. So these are only the 3 possible configuration, and so the omega, the number of microstate is 3. Okay, do you understand what the microstate means? So basically microstates are number of possible configuration that the system has. Okay, so it's a very simple example to show that. So basically these are the 3 microstates. 2, 2, yeah. Okay, this is a simple one. Now let's go to the next problem. Okay, this is little bit involved, so but let's try to solve it. Now imagine you have n identical particles in a container of volume V. Okay, you have a container, there are n identical particles, okay, like molecules of a gas or something. Now divide the this volume into cells of size B. So now you want to divide it, okay, so we are dividing it in cells of size of volume B. So total volume is V and the single cell volume is B, and the condition is number of particles should be less than equal to V by B. Okay, that means each cell can either be empty or single, and also the condition given is each cell can be either be empty or be singly occupied. Okay, it cannot have two particles, either it can be empty or one particle will be there inside each cell. Then the question is, what is the number of accessible microstate? Okay, so now if you want to solve this kind of problem, I mean, like we solved before, like we solved the one above, I mean, you will have to count, so you will have to take all the scenarios where here is 1 1 1 1 1, here 0 1 1 1 1, and then you have I don't know how many particles are there, and it becomes too complicated to work it out as we did before. So now here comes the probability theory to save us. Basically, the permutation and combination that we studied in your in our high school and wherever. Okay. Now, one thing here matters is, since these are identical particles, so the order of, the order in which we are placing it inside the cell, it doesn't matter. Okay. So what matters is, we have to select n cells to place the particles. Okay. So total number of cells is, V by B, right? This is the total volume, and we are dividing into volume of B. So this is the total number of cells that are available to distribute n identical particles. Okay. And this is equivalent to, choosing n positions out of V by B positions available. Okay. And which is given by the formula for, permutation and combination, basically this thing. Okay. This is the formula of choosing n positions out of V by B. So the first option here is the permutation formula, which will not work, right? Because you are not just arranging, you are choosing, right? So the correct option is this third one. Is it fine? So this is basically the number of microstate that is available in this system. Okay, thank you. Okay, so let's go to the next problem. So here, consider this is a general statement, and then we have some problem based on it. Okay, so consider a magnetic system with total energy having n spin in a microcanonical ensemble. So microcanonical ensemble we just studied. Okay, the Hamiltonian is given. So the Hamiltonian is given by this box thing, and it is sum over the spin state. So sigma I is plus minus 1 eigenstates of spin operator. Okay, so yeah, so the Hamiltonian is given, and the total energy is E, and there are n particles or spins in the system. Okay, now the question here is, assume that there are n plus up spin and n minus down spin. That is, n plus have sigma I equal to 1 and n minus have sigma I equal to minus 1. And we are asked the expression of n plus and n minus in terms of total energy and total number of spin. Okay, so this is rather very easy, right? So how to write it? I mean, how to do it? So we have, so energy we can write simply from this formula here. So if you have n plus number of spins with plus 1, I mean spin state, and n minus with minus 1 spin state, then the total energy will be, I mean from this Hamiltonian formula, this will be simply n plus minus n minus, right? Is it fine? And we have total number of spin is equal to n plus plus n minus, right? So this corresponds from this formula. Is it fine? So this is the sigma I basically. For the up spin we have plus 1, for the down spin we have minus 1. That's what I used to calculate the total energy. Okay, and if you solve these two equations, so equation 1 and equation 2, if you just solve these two equations, you will find, I mean you have to just, because there are two equations, two unknowns, n plus and n minus, you can solve it and you can write the expression for n plus and n minus like this. Is it fine? Is it fine, or should I derive it explicitly? Simple, right? You add these two equations and then you subtract it. And you will get these two. Okay. So the correct answer is this one. Yeah. Okay, now let's move to the next question. So for the same kind of for the same configuration, okay, here it is asking the total number of microstates accessible to the system. Now how to calculate this? Any idea? So you have n spins, okay, there are n plus up spin, n minus down spins. That's it, that you know, okay. I mean this can either go to this can either be up spin or either can be I mean down spin. And so what is the total number of microstate? I mean what is the number of different number of ways to arrange these spins? Do you have any idea? Okay, I'll ask a simpler question. No, just now forget this, okay? There are n spins, there are n particles you have. What is the total number of ways to arrange them? Yeah, n factorial, great. Okay, now out of these, if you have n plus and n minus particles which are of the same kind, right, they are identical, these n minus n plus particles are identical, n minus are identical. Now then what will be the total number of ways to arrange them? You will have to divide by these two numbers, right? Sorry, am I right? And this is the number of microstate, and you can just put this expression of n plus and n minus here, and the answer is 2. Yeah, sorry, it's not 2. Yeah, 2, sorry. Yeah, great. Okay, easy one, right? Okay, now let's go to the fifth question. Okay, now just we have learned this, right, the entropy. So here it is asking entropy per spin of the system. That means entropy density kind of thing, entropy per particle per spin, okay. And so in the thermodynamic limit it is asking. So yeah, I mean we can use this limit that when energy and number tends to infinity, and so this is the thermodynamic limit, okay. So total energy and number of particles, we consider them infinity, and this is the energy density U. Okay, why it is given, I'll just show you. So we know that entropy is given by this, right? And we want to calculate the number of micro, and we know the number of microstate we just calculated here, right? So if you just blindly put that, it will be, you know, n factorial, n plus factorial, n minus factorial. So basically this is the answer. But in the thermodynamic limit, so if your n is infinity, this can be written, I mean, you can open up the log, a logarithmic, so this is k ln minus, okay, minus ln plus factorial, sorry, let me write it again. Let me know if you don't understand what I'm doing. I'm just expanding. I'm just because you know that log of AB is equal to log of A plus log of B. You know this, right? So factorial minus log of n plus factorial minus log of n minus factorial. Okay. If so, there is a approximation called Stirling approximation. What Stirling approximation tells you is that if n tends to infinity, okay, then log of n factorial is equal to n log n minus n plus 1. Okay, do you know this? This is a, I mean, this can be derived, it is a very basic thing in statistical mechanics, I mean thermodynamics. Okay, so this is what is called a Stirling limit, and this you can use here, and if you use that there, what you get is so basically ln of, I mean ln, so entropy will be n ln n minus n plus ln n plus minus n minus ln n minus, and here we have used that n is equal to n plus n minus. Okay, oh sorry, there will be a because of this plus 1, there will be a plus 1 here, and then minus 1 from here and here, so this will be minus 2, and so you will have a plus 1 here, right? Sorry, minus 1 here, right? Is that fine? Okay, you are saying that the plus 1 is plus 1 should not be there. I remember plus 1 something, but yeah, I might be wrong. Okay, let me. I'll check it. But okay, yeah. If we remove this, then I think it's fine. Yeah. So yeah. So then now substitute n plus and n minus from what we have derived here. Okay. And if you substitute that and you do some arithmetic, you will find that s is equal to just k ln 2 minus 1/2, and we are using you know, E by N is equal to U, the energy density. Okay, ln 1 minus U by mu h. It's a very long expression. Half 1 plus U mu h ln 1 plus U by mu h. Yes, this is the answer, which is this. Sorry, which is this? Which one? Yeah. Minus minus plus plus. This one. These two. Wait. Oh, minus. No, not this one. It is the first one. Here is the minus sign. Yeah. Okay. Is it fine? Yeah. Just make sure what is the Stirling approximation. I think it is. It is not plus one. I'll have to check. Yeah. Okay. Okay, so this is another problem. Then let's move to our next problem. Yeah. So here what it asks is, using the above expression, what is the temperature of the spin system? Any idea how to find the temperature? So now we have the entropy, the expression for entropy, right? And we are so now you see, from the microscopic picture we have come to the macroscopic picture. We have calculated entropy. Okay, we had just a system of spins, right? So how we started out? So we had just a sorry, where it is? Yeah. Yeah, we just had a system of spins. Energy was given, and we just calculated, what we calculated. We just calculated the microstate available, and from there we calculated the entropy, and now from the entropy we can calculate the temperature of the system. Isn't it interesting? Right? How we can calculate the temperature of the system? Anyone? What is the formula? From first law of thermodynamics, right? This is the formula. And if you differentiate this, so this is your entropy. It is already as a function of U, the internal energy, right? And if you just differentiate it, you will get this. So you should try it. It's very simple to do. Sorry. U by mu h, and then there will be minus U by mu h. Okay. And so temperature will be simply 2 mu h by kb ln of 1 plus U by mu h and 1 minus U by mu h inverse. Okay, so which is the correct answer? Okay, yeah, so you can take this in minus sign. So which is the correct answer? This, wait, yeah, this one, second one, right? No, there is a two factor, sorry, not this one. This one. Wait, did I do something wrong? If you differentiate it, this one goes to 0. Then you have, yeah, with negative sign, yeah, with negative sign you should have this. So, wait, why I am writing 2? Okay, just check. I think the 2 factor will not be there. So this will be the correct answer anyway. Just check once, okay? Okay, so let's do the last problem. Now we have the temperature. Now what we can do is we can find the equation of state for the magnetization. So for an ideal gas we have this equation of state, right? Similarly, for the system of spin we can have the equation of state in terms of magnetization, temperature, and it's what else? It's yeah, H. So the H is the Hamiltonian basically. I mean energy basically. So and how to do that? So we know that the Hamiltonian is given by this, right? And magnetization, you know that it is given by this mu n, right? Mu is the mu is basically what it is called, the constant, the permeability or something. Yeah, permeability. Yeah. So magnetization is basically this, and here since this spin up for spin up particles it is positive, spin down it is negative. So that's why mu n plus minus n minus. And magnetization per spin is m by n. So mu n plus n minus n plus minus n minus divided by n. And yeah, so this is that. And total energy, we written it earlier, it is this quantity, and from here you can write n plus minus n minus is equal to E by mu h, and if you substitute it here, so your magnetization is minus E by n h, right, which is minus u by h, because E by n is u, right? Now you have this expression which is temperature in terms of u. Now you can invert this equation to get u as a function of temperature. So to do that, I mean you can basically choose x is equal to u by mu h, okay, so that what you have now is ln 1 plus x 1 minus x, okay, is equal to 2 mu h by kBt, and then 1 plus x 1 minus x is equal to, so I am taking the exponential on both sides, so the log will go away and here will be an exponential kBt, and basically then if you solve for x you will get stan h. Okay, and so the answer is, so basically m by mu is equal to tan h mu h kbt, okay, which gives you this thing. So m is equal to mu tan h mu h kbt, okay, where we have used that so tan minus, I mean this negative sign will be I think it can be consumed inside yeah, it can be consumed inside tan h. So this is the correct answer. Sorry, this one. This. Yeah, this is these all are arithmetic. What matters is that I mean from from just the knowledge of number of spins, we are able to and Hamiltonian, obviously we are able to calculate the equation of state, entropy, temperature, everything, right? And so this is the power of statistical mechanics. If you can write out the number of microstate, then you can do anything. You can calculate entropy, you can calculate temperature, you can relate thermodynamics with macro states of the system. Yeah. So here one thing is that this mu h is called something called Zeeman energy, okay? It has a special name. Zeeman energy. And this kbt is called the thermal energy, right? You know that kbt is thermal energy. So this magnetization is depends on the ratio of Zeeman to thermal energy. And if you want to like understand more, so this is basically competition between order and disorder, okay? Okay. So do you have any question till now? You guys understood everything? So this was the last problem that I had to discuss today. Is it fine? If you have any question, please ask. Okay, thank you. If you don't have any question, then let's close the session and meet next week. So thank you for joining. Bye. Bye.